When a pathogen breaches a host, its priority is survival. The virus rapidly replicates inside host tissue, destroying cells and triggering an immune response. To confirm the identity of the attacker, veterinarians often rely on molecular testing, like PCR. These tests search directly for the pathogen's DNA or RNA within the bird. But molecular tests have a strict expiration date. Once the host's immune system successfully clears the virus, the genetic material disappears, creating a complete diagnostic void. Weeks later, a farm manager might notice a sudden drop in egg production, severe respiratory issues, or swollen heads in the flock. By then, running a PCR test is useless. The active virus is already gone. Knowing what pathogen is present today cannot explain the damage done yesterday. To solve these late-stage clinical cases, veterinarians must look backward to reconstruct the flock's hidden biological timeline. That reconstruction requires serology. In avian pathology, serology is defined strictly as the in vitro examination of interactions between antigens and antibodies. While a virus is physically eliminated from the body, the immune system's response to it is not. Specific antibodies continue to circulate in the blood long after the pathogen is destroyed, serving as a permanent chemical memory. To read that memory, pathologists use quantitative tools like the enzyme-linked immunosorbent assay, or ELISA. By processing serum in a 96-well laboratory microplate, they can count the exact number of lingering antibodies. This capability divides the science into two distinct branches: serodiagnosis, which investigates the historical cause of an active illness, and serological monitoring, which evaluates a farm's biosecurity and the efficacy of its vaccines. However, the most sophisticated laboratory equipment in the world cannot fix a flawed sample. The mathematical accuracy of the final laboratory result is entirely dependent on how the blood is physically collected on the farm. Consider a scenario where two batches of samples from the exact same flock are sent to a lab, and they return completely contradictory results regarding the flock's immune status. This failure happens because of runaway variability. In a massive commercial house, environmental deviations, like a partially blocked drinker line, can cause birds in one section to ingest significantly less vaccine than birds in another. If a farm worker only samples birds from the side of the house with the broken drinker, the resulting data will falsely suggest the entire flock is completely unprotected. To neutralize this environmental bias, sampling must follow a strict geometric grid. In a standard 80-meter house, testing nodes are spaced evenly every 7 to 8 meters along the diagonals, generating a 23-point testing grid. The target pathogen type dictates the density of this grid. Diagnosing a viral infection requires those 23 points, while mapping a bacterial infection requires a denser matrix of 60 individual samples. This structured randomization ensures every individual bird has an equal mathematical chance of being selected. It is the only way to average out local deviations and produce an accurate numerical reflection of the entire flock. Even within that randomized grid, specific individuals must be excluded. Birds with active diarrhea, physical deformations, or severe dehydration will skew the data and should never be sampled. The extraction itself must take place outside the production house to avoid environmental contamination. The ideal candidates are average-sized individuals, preferably fasting at the time of the draw. When testing day-old chicks, the physiological baseline is extremely rigid. A valid subject must weigh exactly 35 to 42 grams, maintain a body temperature of 37.7 degrees Celsius, and show absolutely zero signs of umbilical inflammation. The blood collection protocol scales with the age of the bird. For chicks under 7 days old, blood is drawn directly from the heart or via decapitation. For birds older than 14 days, the standard approach targets the wing vein. From each bird, the technician must extract 1 to 3 milliliters of whole blood. This volume ensures enough raw material survives the laboratory preparation. Once collected, the whole blood is loaded into a centrifuge rotor. The rotational force separates the heavy red blood cells from the lighter, clear fluid. The result of this separation is exactly 0.5 to 0.75 milliliters of pure serum. Securing this exact yield is the fundamental physical requirement for moving the investigation from the farm to the laboratory. With the pure serum prepared, the testing must answer 3 distinct questions. What specific antibodies are present? how many of them are there, and how effective are they. This table categorizes the primary diagnostic tests used in avian pathology, matching HI, AGP, and ELISA assays to the specific antibody classes they detect. The ELISA test answers the question of quantity, counting the total number of long-living IgY and early response IgM antibodies present. Moving to the top row, the hemagglutination inhibition test serves a different function. It measures actual neutralizing activity against specific viral targets like Newcastle disease. Choosing the right test matters because pathogens vary in their seroantigenicity, their ability to provoke an immune response. A flock might suffer severe clinical symptoms of infectious bronchitis, but still return low sensitivity results on older qualitative tests like agar gel precipitation. Laboratories must also account for cross-reactions. In these cases, high concentrations of one antibody might falsely trigger a positive test result for a completely different but structurally related pathogen. Because no single diagnostic assay is flawless, rigorous infectious immunology relies on cross-verification. Pathologists routinely run both an ELISA and an HI test on the exact same serum, ensuring the output represents the biological truth. Once the laboratory generates the raw numerical data, the final analytical step is aligning that output against the biological timeline of the infection. This graph maps the chronological life cycle of an infection, tracking the rise and fall of DNA, RNA, IgM, and IgY concentrations over the days following the onset of clinical symptoms. During the first phase, marked by the leftmost peak, the pathogen's genetic material is actively replicating. This narrow window is the only time a PCR test will return a true positive result. As the host fights back, the DNA and RNA levels drop. This decline intersects directly with a rapid, short-term rise in specific IgM antibodies, marking the acute phase of the immune response. Finally, as the IgM response fades, the long-living IgY antibodies emerge. As shown on the right side of the timeline, this IgY curve remains elevated indefinitely, providing a strong signal long after molecular tests fail. By identifying exactly which of these specific markers is currently peaking in the serum, a pathologist can calculate the precise number of days that have passed since the pathogen first entered the flock. To interpret these concentrations, pathologists rely on strict mathematical thresholds. The most basic is the cutoff titer, the baseline numerical value at which a test result flips from formally negative to positive. From there, the values diverge based on intent. A protective titer is the proven baseline required to show that a vaccine is actively defending the birds, while a diagnostic titer is a much higher spike that confirms a harmful active infection. This chart displays an aggregate summary report from IDEXX software, analyzing 851 samples from one-day-old broiler chicks. Processing data through specialized databases allows managers to establish highly specific, localized baselines for their farm, rather than relying on generic regional standards. During a critical investigation, consistency in data processing is vital. Switching testing laboratories mid-analysis can introduce up to a 25% variance in titer levels for the exact same serum. Even with perfectly consistent data, serology has a strict biological limitation. The test accurately counts antibodies, but it indisputably cannot distinguish whether those antibodies were created by a destructive field strain or a harmless live vaccine. Therefore, a single high titer provides no context. To prove an active spreading infection, diagnostic serology requires the paired serum rule, drawing two sets of samples weeks apart to confirm an escalating antibody count. Ultimately, absolute antibody numbers alone do not diagnose a disease. The physical reality of the flock, the presence and severity of the clinical symptoms, must dictate the conclusion. Serology is the mathematical tool used to verify the parameters of that historical event.